Best practices. The use of observability. 1. Know you carry out an audit of the platform. Turn on data and translate the data into a SPI of any use. It is sent what seems unimportant to these patterns and abnormalities so the platform can report what it sees. Systems such as Splunk, Datadog and Mesmo, previously logged DNA, have shown how data can be centralized and used to provide observability insights. 5. Data analysis tools should fit the purpose. Analysis tools that don't pick up on key areas, such as early-stage problems or zero-day attacks on the platform, won't provide the peace of mind an effective observability system offers. Most observability approaches are coalescing around systems such as security information and event management products from the likes of Logarithm, FireEye or Sumo Logic. These products, built on a need for organizations to secure their platforms against internal and external threats, are rapidly recognizing they have the capabilities to become observability offerings and can use their pattern recognition and advanced heuristic systems to identify other issues, such as early-stage problems at a virtual or physical level across an IT platform. 6. Report in the right manner. Observability shouldn't be seen as a tool only for sysadmins or DevOps practitioners, but as a means of breaching the chasm between IT and the business by reporting what it sees and advising on what needs to be done. Reporting should inform IT professionals in real time as to what problems are present and provide trend analysis and business impact reporting that can be understood by line of business personnel. 7. Integrate with automated remediation systems wherever possible. Many issues identified by an observability offering will be relatively low level. Most sysadmins will already have tooling in place to automatically fix issues such as systems requiring patching or updating, or where extra resources must be applied to a workload. By integrating an observability system into these tools, IT can more easily maintain an optimized environment. Where automation isn't possible, having such a filter ensures IT can focus on more important problems and fix them more quickly. 8. Feedback loops should be present and effective. Repeated security issue identification or resource problems might be caused by coding issues or implementation that can't be fixed through automated means. Tying observability systems into help desk and trouble ticketing offerings ensure areas are picked up and assigned to the right IT staff. Observability is becoming a necessity as organizations move to a more decentralized IT platform. Without the capability to aggregate and analyze data coming from all areas of an IT platform, organizations open themselves up to problems ranging from inadequate application performance through a poor user experience to major security issues. In the long term, observability will differentiate how well organizations perform in a highly dynamic and complex world.
Procedural language. What does procedural language mean? A procedural language is a type of computer programming language that specifies a series of well-structured steps and procedures within its programming context to compose a program. It contains a systematic order of statements, functions and commands to complete a computational task or program. Procedural language is also known as imperative language. A procedural language, as the name implies, relies on predefined and well-organized procedures, functions or subroutines in a program's architecture by specifying all the steps that the computer must take to reach a desired state or output. The procedural language segregates a program within variables, functions, statements and conditional operators. Procedures or functions are implemented on the data and variables to perform a task. These procedures can be called / invoked anywhere between the program hierarchy, and by other procedures as well. A program written in procedural language contains one or more procedures. Procedural language is one of the most common types of programming languages in use, with notable languages such as C, C++, Java, ColdFusion and Pascal.
Kubernetes. BB. Kubernetes, also known as K8s, is an open-source system for automating deployment, scaling, and management of containerized applications. It groups containers that make up an application into logical units for easy management and discovery. Kubernetes builds upon 15 years of experience of running production workload at Google, combined with best-of-breed ideas and practices from the community. Plain scale. Designed on the same principles that allow Google to run billions of containers a week. Kubernetes can scale without increasing your operation team. Whether testing locally or running a global enterprise, Kubernetes flexibility grows with you to deliver your applications consistently and easily no matter how complex your need is. Run K8s anywhere. Kubernetes is open source, giving you the freedom to take advantage of on-premises, hybrid, or public cloud infrastructure, letting you effortlessly move workloads to where it matters to you. Kubernetes features: automated rollouts and rollbacks. Kubernetes progressively rolls out changes to your application or its configuration, while monitoring application health to ensure it doesn't kill all your instances at the same time. If something goes wrong, Kubernetes will roll back the change for you. Take advantage of a growing ecosystem of deployment solutions. Storage orchestration. Automatically mount the storage system of your choice, whether from local storage, a public cloud provider such as AWS or GCP, or a network storage system such as NFS, ISC, Ceph, Cinder. Secret and configuration management. Deploy and update secrets and application configuration without rebuilding your image and without exposing secrets in your stack configuration. In addition to services, Kubernetes can manage your batch and C workloads, replacing containers that fail, if desired. IP4 IP6 dual stack. Allocation of IP4 and IP6 addresses to pods and services. Service discovery and load balancing. No need to modify your application to use an unfamiliar service discovery mechanism. Kubernetes gives pods their own IP addresses and a single DNS name for a set of pods, and can load balance across them. Self-healing. Restarts containers that fail, replaces and reschedules containers when nodes die, kills containers that don't respond to your user-defined health check, and doesn't advertise them to clients until they are ready to serve. Automatic bin packing. Automatically places containers based on their resource requirements and other constraints, while not sacrificing availability. Mix critical and best effort workloads in order to drive up utilization and save even more resources. Horizontal scaling. Scale your application up and down with a simple command, with a UI, or automatically based on CPU usage. Designed for extensibility. Add features to your Kubernetes cluster without changing upstream source code. What is a REST API? A REST API, also known as RESTful API, is an application programming interface, API or web API, that conforms to the constraints of REST architectural style and allows for interaction with RESTful web services. REST stands for Representational State Transfer and was created by computer scientist Roy Fielding. What's an API? An API is a set of definitions and protocols for building and integrating application software. It's sometimes referred to as a contract between an information provider and an information user, establishing the content required from the consumer, the call, and the content required by the producer, the response. For example, the API designed for a weather service could specify that the user supply a zip code and that the producer reply with a two-part answer, the first being the high temperature, and the second being the low. In other words, if you want to interact with a computer or system to retrieve information or perform a function, an API helps you communicate what you want to that system so it can understand and fulfill the request. You can think of an API as a mediator between the users or clients and the resources or web services they want to get. It's also a way for an organization to share resources and information while maintaining security, control, and authentication, determining who gets access to what. Another advantage of an API is that you don't have to know the specifics of caching, how your resource is retrieved or where it comes from. REST is a set of architectural constraints, not a protocol or a standard. API developers can implement REST in a variety of ways. When a client request is made via a RESTful API, it transfers a representation of the state of the resource to the requester or endpoint. This information, or representation, is delivered in one of several formats via HTTP, JSON, JavaScript Object Notation, HTML, XLT, Python, PHP, or plain text. JSON is the most generally popular file format to use because, despite its name, it's language agnostic, as well as readable by both humans and machines. Something else to keep in mind, headers and parameters are also important in the HTTP methods of a RESTful API HTTP request, as they contain important identifier information as to the request's metadata, authorization, uniform resource identifier, URI, caching, cookies, and more. There are request headers and response headers, each with their own HTTP connection information and status codes. In order for an API to be considered RESTful, it has to conform to these criteria. First, a client-server architecture made up of clients, servers, and resources, with requests managed through HTTP. Second, stateless client-server communication, meaning no client information is stored between GET requests and each request is separate and unconnected. Third, cacheable data that streamlines client-server interactions. Fourth, a uniform interface between components so that information is transferred in a standard form. This requires that a. Resources requested are identifiable and separate from the representations sent to the client. B. Resources can be manipulated by the client via the representation they receive because the representation contains enough information to do so. C. Self-descriptive messages returned to the client have enough information to describe how the client should process it. D. Hypertext/hypermedia is available, meaning that after accessing a resource the client should be able to use hyperlinks to find all other currently available actions they can take. Fifth, a layered system that organizes each type of server, those responsible for security, load balancing, etc., involve the retrieval of requested information into hierarchies, invisible to the client. 6. Code on demand, optional, the ability to send executable code from the server to the client when requested, extending client functionality. Though the REST API has these criteria to conform to, it is still considered easier to use than a prescribed protocol like SOAP, Simple Object Access Protocol, which has specific requirements like XML messaging, and built-in security and transaction compliance that make it slower and heavier. In contrast, REST is a set of guidelines that can be implemented as needed, making REST APIs faster and more lightweight, with increased scalability, perfect for Internet of Things, IoT, and mobile app development. REST versus SOAP. Overview. REST and SOAP are two different approaches to online data transmission. Specifically, both define how to build application programming interfaces, APIs, which allow data to be communicated between web applications. Representational State Transfer, REST, is a set of architectural principles. Simple Object Access Protocol, SOAP, is an official protocol maintained by the World Wide Web Consortium, W3C. The main difference is that SOAP is a protocol, while REST is not. Typically, an API will adhere to either REST or SOAP, depending on the use case and preferences of the developer. REST, Representational State Transfer. REST is a set of architectural principles attuned to the needs of lightweight web services and mobile applications. Because it's a set of guidelines, it leaves the implementation of these recommendations to developers. When a request for data is sent to a REST API, it's usually done through Hypertext Transfer Protocol, commonly referred to as HTTP. Once a request is received, APIs designed for REST, called RESTful APIs or RESTful Web Services, can return messages in a variety of formats: HTML, XML, plain text, and JSON. JSON, JavaScript Object Notation, is favored as a message format because it can be read by any programming language, despite the name, is human and machine readable, and is lightweight. In this way, RESTful APIs are more flexible and can be easier to set up. An application is said to be RESTful if it follows 6 architectural guidelines. A RESTful application must have 1. A client-server architecture composed of clients, servers, and resources. 2. Stateless client-server communication, meaning no client content is stored on the server between requests. Information about the session state is instead held with the client. 3. Cacheable data to eliminate the need for some client-server interactions. 4. A uniform interface between components so that information is transferred in a standardized form instead of specific to an application's needs. This is described by Roy Fielding, the originator of REST, as the central feature that distinguishes the REST architectural style from other network-based styles. 5. A layered system constraint, where client-server interactions can be mediated by hierarchical layers. 6. Code on demand, allowing servers to extend the functionality of a client by transferring executable code, though also reducing visibility, making this an optional guideline. SOAP, Simple Object Access Protocol. SOAP is a standard protocol that was first designed so that applications built with different languages and on different platforms could communicate. Because it is a protocol, it imposes built-in rules that increase its complexity and overhead, which can lead to longer page load times. However, these standards also offer built-in compliances that can make it preferable for enterprise scenarios. The built-in compliance standards include security, atomicity, consistency, isolation, and durability, ACID, which is a set of properties for ensuring reliable database transactions. Common web service specifications include 1. Web Services Security, WS Security, standardizes how messages are secured and transferred through unique identifiers called tokens. 2. WS Reliable Messaging, standardizes error handling between messages transferred across unreliable IT infrastructure. 3. Web Services Addressing, WS Addressing, packages routing information as metadata within SOAP headers, instead of maintaining such information deeper within the network. 4. Web Services Description Language, WSDL, describes what a web service does, and where that service begins and ends. When a request for data is sent to a SOAP API, it can be handled through any of the application layer protocols, HTTP, for web browsers, SMTP, for email, TCP, and others. However, once a request is received, returned SOAP messages must be returned as XML documents, a markup language that is both human and machine readable. A completed request to a SOAP API is not cacheable by a browser, so it cannot be accessed later without resending to the API. SOAP versus REST. Many legacy systems may still adhere to SOAP, while REST came later and is often viewed as a faster alternative in web-based scenarios. REST is a set of guidelines that offers flexible implementation, whereas SOAP is a protocol with specific requirements like XML messaging. REST APIs are lightweight, making them ideal for newer contexts like the Internet of Things, IoT, mobile application development, and serverless computing. SOAP web services offer built-in security and transaction compliance that align with many enterprise needs, but that also makes them heavier. Additionally, many public APIs, like the Google Maps API, follow the REST guidelines. Let's imagine you are building an online store that uses the microservice architecture pattern and that you are implementing the product details page. You need to develop multiple versions of the product details user interface. 1. HTML5 JavaScript-based UI for desktop and mobile browsers. HTML is generated by a server-side web application. 2. Native Android and iPhone clients. These clients interact with the server via REST APIs. In addition, the online store must expose product details via a REST API for use by third-party applications. A product details UI can display a lot of information about a product. For example, the Amazon.com details page for Pojo's in-action displays. 1. Basic information about the book such as title, author, price, etc. 2. Your purchase history for the book. 3. Availability. 4. Buying options. 5. Other items that are frequently bought with this book. 6. Other items bought by customers who bought this book. 7. Customer reviews. 8. Sellers ranking. Since the online store uses the microservice architecture pattern, the product details data is spread over multiple services. For example, 1. Product info service, basic information about the product such as title, author. 2. Pricing service, product price. 3. Order service, purchase history for product. 4. Inventory service, product availability. 5. Review service, customer reviews. Consequently, the code that displays the product details needs to fetch information from all of these services. Problem. How do the clients of a microservices-based application access the individual services? Forces. 1. The granularity of APIs provided by microservices is often different than what a client needs. Microservices typically provide fine-grained APIs, which means that clients need to interact with multiple services. For example, as described above, a client needing the details for a product needs to fetch data from numerous services. 2. Different clients need different data. For example, the desktop browser version of a product details page desktop is typically more elaborate than the mobile version. 3. Network performance is different for different types of clients. For example, A mobile network is typically much slower and has much higher latency than a non-mobile network. And, of course, anyone is much slower than a LAN. This means that a native mobile client uses a network that has very different performance characteristics than a LAN used by a server-side web application. The server-side web application can make multiple requests to back-end services without impacting the user experience, whereas a mobile client can only make a few. 4. The number of service instances and their locations, host plus port, changes dynamically. 5. Partitioning into services can change over time and should be hidden from clients. 6. Services might use a diverse set of protocols, some of which might not be web-friendly. Solution: implement an API gateway that is a single entry point for all clients. The API gateway handles requests in one of two ways. Some requests are simply proxied/routed to the appropriate service. It handles other requests by fanning out to multiple services. Rather than provide a one-size-fits-all style API, the API gateway can expose a different API for each client. For example, the Netflix API gateway runs client-specific adapter code that provides each client with an API that's best suited to its requirements. The API gateway might also implement security, for example, verify that the client is authorized to perform the request. Variation: backends for frontends. A variation of this pattern is the backends for frontends pattern. It defines a separate API gateway for each kind of client. In this example, there are three kinds of clients: web application, mobile application, and external third-party application. There are three different API gateways. Each one provides an API for its client. Examples: Netflix API gateway. A simple Java/Spring API gateway from the money transfer example application. Resulting context: using an API gateway has the following benefits. Insulates the clients from how the application is partitioned into microservices. Insulates the clients from the problem of determining the locations of service instances. Provides the optimal API for each client. Reduces the number of requests/round trips. For example, the API gateway enables clients to retrieve data from multiple services with a single round trip. Fewer requests. Also means less overhead and improves the user experience. An API gateway is essential for mobile applications. Simplifies the client by moving logic for calling multiple services from the client to API gateway. Translates from a standard public web-friendly API protocol to whatever protocols are used internally. The API gateway pattern has some drawbacks. Increased complexity. The API gateway is yet another moving part that must be developed, deployed and managed. Increased response time due to the additional network hop through the API gateway. However, for most applications the cost of an extra round trip is insignificant. Issues. How implement the API gateway? An event-driven/reactive approach is best if it must scale to handle high loads. On the JVM, NIO-based libraries such as Netty, Spring Reactor, etc. make sense. Node.js is another option. Related patterns. The microservice architecture pattern creates the need for this pattern. The API gateway must use either the client-side discovery pattern or server-side discovery pattern to route requests to available service instances. The API gateway may authenticate the user and pass an access token containing information about the user to the services. An API gateway will use a circuit breaker to invoke services. An API gateway often implements the API composition pattern. Known uses. Netflix API gateway. Example application. See the API gateway that part of my microservices patterns example application. It's implemented using Spring Cloud Gateway. Day what? Day 24. PSK, pre-shared key. PSTN, public switch telephone network. PTP, point-to-point. PTR, pointer. PUA, privileged user agreement. PVC, permanent virtual circuit. QoS, quality of service. QSFP, quad small form factor pluggable. Radius, remote authentication dial in user service. RARP, reverse address resolution protocol. RAS, remote access service. IDEA on repeat. Edge service. An edge service is a component which is exposed to the public internet. It acts as a gateway to all other services, which we will refer to as platform services. For example, consider NGINX reverse proxy in front of some web resource servers. Here, NGINX acts as an edge service by routing public HTTP requests to the appropriate platform service. An example edge service could be NGINX as a reverse proxy for two resource servers. Requests for images are routed to image server, while requests for text are routed to text server. The reverse proxy pattern makes sense if every one of your resource servers is hardened to receive raw internet traffic. But in the typical service-oriented architecture, implementing a simple reverse proxy would duplicate a substantial amount of security and reliability code across platform services. For example, we do not want to re-implement user authentication in each platform service. Instead, we factor these responsibilities directly into the edge service. It validates and authenticates incoming requests. It enforces rate limits to protect the platform from undue load, and it routes requests to the appropriate upstream services. Factoring these high-level features into the edge service is a huge win for platform simplicity.
I met you in the summer, when you left it was cold. Said we loved one another.